Hello, everyone. Thank you for joining this webinar session. Let's wait for a couple of minutes to let people join this webinar session, and after we can start. Thank you for your understanding. Okay, now we can start. Thank you for your patience and joining this webinar organized by Genesink about eco-design. So I am Benjamin DHUIEGE. I am the head of R&D at Genesink, and I will be one of your speakers for this webinar today. I have a PhD in material science and chemistry, and I'm here today with my colleague Guillaume.
Hello, I'm Guillaume CROCHET. I'm an R&D project manager at Genesink, and I have a PhD in physics and material chemistry.
So the agenda of this webinar today would be as follow. We will first present Genesink company. We will introduce afterwards the eco-design, the basics of the eco-design. Then we will present and describe some use cases from Genesink using the principle of the eco-design for our technologies. We will finally conclude about it and do two different sessions. The first one we will ask you for some question, and the last one is about the question and answer session. So you have a chat box on this in a window with the chat. Then you can ask your question, and we will answer them during this session. The webinar will be also recorded, and you will be able to access the presentation and the replay of this webinar afterwards on demand. So first, you may wonder if who is Genesink. So Genesink is one of the world industrial leader in nano inks, with more than 80 nano solutions already available at ton scale and out of the shelf. The company was created in 2010. We are located in the south of France, near Aix-en-Provence and Marseille, which is called La Provence. We have already 12 patent families granted, with represented over more than 100 patents worldwide. Actually, we are around 20 talented people in the company, located in different areas of the world, because we are working globally with different sales representatives in different regions of the world, especially in Europe, USA, Taiwan, and Japan, for instance. So our technology is present everywhere in electronics. Our technology can be summarized in 5 points. We first are and developed hyper specialty chemicals with conductive and semiconductive solutions to enable the design of next generation of consumer electronics products. Secondly, we used a unique process based on additive manufacturing that yields very high conductivity for the electronic components. Third, we are using this additive manufacturing as a substitute of the EV and polluting production techniques that is actually used in electronic industry. Fourth, we empower the additive manufacturers with better performance, and by which is the main important point here is that we use less raw material to do this. And finally, we tailor our solutions to our customers with specific needs at their manufacturing location of choice.
So let's deep dive a little bit more in eco-design. So what is the eco-design? There are several definitions, but one is that eco-design is the integration of environmental aspects into product design and development with the aim of reducing adverse environmental impacts throughout a product's life cycle. Basically, what it means that if you want to produce one product, for example, starting from the thinking of the project, you can impact greatly with eco-design each step of the product. From the raw material, for example, in Genesink, since we are producing ink, we are rarely at the end of life cycle. So the raw material aspect is important to us. There is no point in taking raw material from, I don't know, the farthest place possible to bring it into France and then ship the product back, well, to another location far away. So you can have a really great impact by selecting the places you choose your raw material, but also the manufacturing in itself, the regions that you're going to use, the solvents that you're going to use can have a large impact on the ecological and economical aspects of the products. So why use the eco-design in itself? So the most popular view nowadays is that recycling is the only option that we have to basically save humankind from all the ecological problems that we have. So it is partially true because eco-design intervene, as I showed you before, at each steps, recycling being only the last one of it. So the interest in doing eco-design first is ecological and economical. Why? Because by thinking, well, differently and having other regions use and other places as places from the raw material, you can then use less water, for example, less raw material and less energy, which is very important nowadays. Then the second and third aspect is that it gives a positive image and innovative one. No one will ever tell you that doing something greener is bad. And then finally, and it's also a very important point, it allows you to anticipate the regulation change of, for example, the REACH regulation or ISO regulation. And this means that you'll never be pushed hard to change the product that works, and you can then have some step forwards to prevent that changes. But nothing is all rainbow and sunshine, so there are also cons doing eco-design. First one is that it is time consuming. If you have something that is working, it will require way much more time to, well, obtain the final product that you had in the first place by eco-designing your synthesis and stuff. Then you'll have also to do a life cycle analysis and study, which will take also time and are usually complicated to complete. And then finally, change in itself. Well, as I said, there is always hard. It's always hard to change something that is working and bringing money into the company to start from scratches and change it all. So what is a life cycle analysis? Then it's divided in basically three parts. The first one is the frame, which englobes the aim of and objectives of the project and the targets. For example, as I showed you in previous slide, we have separate steps. For example, the synthesis of the nanoparticles and also the formulation of the ink. So you can, well, basically aim for only either the impact of the synthesis or the impact of the formulation or both of it. So it's very important to select what are the objectives of your life cycle analysis. Then the second one is the life cycle inventory, which is the hardest point. You have to collect the data of everything that you are using and everything you want to use and compare it to, well, the working process that you have. And sometimes it's quite hard because the data collected are not always complete and you have to, well, search for different database and it gets harder. but it is a job in itself. So, well, I think it's okay. And then finally, the analysis of the life cycle environment impacts. It means that you'll have targeted impacts that you can, well, look closer. For example, the waste of water that you're using, the pollution of soils, the pollution of air, the impact on the human safety, for example. So there are several impacts that you can target to see if you are improving the process that you already have by eco-designing it. So what about the eco-design in Genesink and our Genesink? Well, we have three different families. We have the Smart Ink family, which is silver conductive nano inks, Transductive one, transparent conductive nano inks, and then finally the Helios ink, which englobes the oxide metallic inks with zinc oxide doped, and tungsten oxide. So we started a project which is called EcoZink, and we decided then to focus on already one well-finished end product, the zinc oxide, and try to eco-design it. So this is a perfect eco-design cycle for the EcoZink project. You basically change the synthesis of the nanoparticles to something greener. Then you also change the solvent, for example, used during the ink formulation by something also greener. And then since we are, well, selling these inks to customers for OLED and OPV devices, well, you can think about working with the partners at the end and obtain the recycling of the products and try to, well, have some sort of a closed loop. So in our case, we worked on the zinc oxide ink, and basically one of the most harmful reagents that you're using during this is usually the solvents. In our case, zinc oxide is produced with methanol. So if you want to eco-design that, you have to change from that virgin methanol that you have to something else. And two choices are possible. The first one is using recycled methanol. And the second one is basically switching the solvent to ethanol or bioethanol. So each of them, well, comes with pros and cons. And for the recycled methanol, it is a cost-effective method. As long as you're able to build a distillation plant that is almost with a yield of 100%, you basically will be in a closed loop. So you'll never have to add again methanol and buy and add new methanol. But it's still using harmful substances for the people. So you'll have only the impact on the ecological and, well, the economical one, but for the human safety, no. And then if you change from ethanol to bioethanol, well, it is a cheaper solvent first. It is also safer. It has a greener origin, but then it is way more time consuming because if you change one reagent in your recipe, well, you have to go back from the beginning and try to obtain the same object that you had in the first place with the methanol. So we can measure those impacts, as I told you, with the life cycle analysis, and this is what it looks like. So at the end, after all the data collected and, well, the calculation made, you can basically, for example, compare the synthesis of the zinc oxide nanoparticles with standard methanol to the zinc oxide nanoparticles with recycled methanol. And what we observed for 9 different impacts is that out of the 9, 6 changed and were reduced by more than 30%. For example, we had basically no impact on the ozone depletion by changing to recycled methanol, but we had quite a higher changes on acidification, climate change, and resource depletion, for example.
So yes, now we can continue with the second use case. So in the past, we have developed an innovative process based on the surface metallization of flexible substrate, because metals like copper and silver are required in most electronics applications, like antennas, batteries, for instance. These metals are often expensive with limited natural reserves worldwide. So that's why we developed this process in 3 steps. The first one is the deposition of the adhesion primer solution by printing, inkjet printing, for instance, or by spray printed, containing a metal catalyst, and we graft the adhesion primer by photonic annealing. The second step of this process is to reduce the metal salts that is in the primary ink to a metal by reducing baths to activate the surface. And then there is an electroless metallization of copper in an autocatalytic copper salt bath. This process can challenge most of the problems caused by the raw material shortage and environmental impact. For instance, this thin melt process replaced the sulfochromic acid surface etching traditionally employed by metallurgists with the water-based primer solution and environmentally friendly polar solvents. The polymer that is fixed by the light using a low energy lamp. So the grafting is very short with low energy consumption. And in addition to this low energy consumption, we also use additive manufacturing using printed processes like inkjet printed or spray printed that is less energy consuming than just traditional deposition methods like PVD or lithography, for instance. And moreover, the thin solution can deposit a very low thickness of copper with obtaining the highest performance that we can have for the conductive or the circuitry that we can pattern with this process. And compared to the traditional PCBs that required something like 45 to 500 gram per meter square, we use only 9 grams. So it's very, very low amount of copper that we can print on this flexible substrate. And also, even you can say that we are using baths to do this process with the copper salt, for instance. Even if we are using this kind of baths, it's an autocatalytic bath that could be used in almost infinite loop. So with this process, we also do a life cycle analysis, and for this 100% additive solution based on the polar solvent that I mentioned, and compared to the process that is traditionally used in the electronic industry to make the PCBs in electronics. So for this, for instance, with this life cycle analysis and the comparison between the two processes, we can observe that with the innovative process, we can reduce by a factor of 10 to 50 the environmental impact, depending on the impacts that we are looking for. So now we presented to you two different use cases, but it's not the end. We would like, and we have the ambition in our company to do a roadmap with this EcoDesign for all the technologies that we are using at Genesink. So we will adopt this EcoDesign strategy for one of our technology that is based on silver nanoparticles. So with this cycle, we will target the different step of the life of the cycle. The first one would be about the nanoparticle synthesis. So we can replace the chemicals that in the reagent that is used in the synthesis by more eco-friendly ones and non-CMR reagents. For instance, in the literature, we can say that we can synthesize silver nanoparticles with a reaction medium based on honey and distilled water, for instance. We will also target to have an eco-design strategy for the formulation of the inks with the use of non-CMR products and also water and alcohol-based solvents. And finally, we will not end to this. We will also, with our partnership with customer, would like to recycle the silver in PCBs, flexible PCBs or photovoltaics. We have some project in mind where we, with partners in Europe that we would like to also to or over the world to recover the silver tracks after doing the final product with the different processes of recovery of this metal. And with this, we can recover the silver in salt or in powder, then we can reformulate into inks. And we have key partners in this project where we have European Recycling Authority that can guide us and help us to do this kind of projects. So as a conclusion, as you can see, this is in our DNA to do the eco-design since early stage in R&D and to develop innovative product and process towards more sustainable production for the electronic industry, especially. We also participate in the global European Sustainable Development Goals within 5 of them. The first one is dedicated to the good health and well-being. Our innovation paves the way for eco-friendly manufacturing. We have also other goals in gender equality, industry innovation and infrastructure, responsible consumption and production, and also climate action. Just to let you know, and for your information, there is different calls for proposal to help you to fund the eco-design of your technologies. We only show you 3 examples that we have in France and Europe. There is 2 kind of call for proposal like Fili or Perfecto in France with regional or national funding. And we have also the one of the cluster in European funding program, the cluster 5, that is dedicated and devoted to the climate action and to develop innovative product and more sustainable. So that's it for today. You can reach us on LinkedIn. You can also visit our website at genesink.com. And also we have, as I mentioned in the beginning of this presentation, we have different sales offices all over the world, like in Paris, here at Rousset near Aix-en-Provence as a headquarter, and also 3 different offices in Japan, Taiwan, and USA.